All right, we're back. We're on page 3, notes 20, Calc AB. We're doing areas of regions that are bounded by curves. And every problem that we've done so far, if you look at it, basically what we're doing is we could take a horizontal line and pass it through. That's not horizontal, that's vertical. We could take a vertical line and pass it through the region, and the top curve and bottom curve would remain the same the entire way through, right? Top and bottom staying the same all the way through. So these are regions that are called vertically simple. It's a simple region where a vertical line always going to have the same top and bottom. What we want to do now is we want to talk about regions that are horizontally simple. So this is not a horizontally simple region, right? Because if you look, so that, let's say that's horizontal. Let's say this is a horizontal line. The left-hand curve and the right-hand curve are kind of like this and this, right? Left and right, left and right. But as soon as I get here, the left-hand curve has switched to this curve and the right-hand curve is still this. That's not simple because you have to switch. The other region, this region is in no way simple. Like, it's the same curve. What do you even do? We have to do some weird stuff. This actually is horizontally simple. It is also vertically simple. A lot of regions are like that. When that's the case, you should integrate with respect to x. When a region, however, is only one type of simple, you don't have a choice. Well, you have a choice. You have an easy choice and a hard choice, maybe. This region, so we're okay-ish. Not really, because it's like the same curve, but we're almost okay. But then we switched, right? We switched from this being the bottom curve to this being the bottom curve. We don't want that. Horizontal line, on the other hand, look at that. It's never going to switch. The left and the right are always the same. So this is horizontally simple, which means we should probably try to integrate with respect to y. So this is kind of an interesting idea. We can do it though. So, I mean, think about it. What I'm going to do is set up the same sort of thing. I'm going to draw some rectangles here. They're going to be right rectangles, but they might as well be called, like, I don't know, top rectangles. So here's what I mean by that. Here's a rectangle. Here's a rectangle. Rectangle. Look at me drawing rectangles. Okay. All of these rectangles, it's pretty easy to generalize how I would go about. This one's weird. Like there. you get nothing. So it's pretty easy to kind of generalize this, right? Like if I were going to, I would have a delta y. And delta y, we're going from -2 up to 4. So 4 minus -2. And then I would just divide it into as many as I wanted. So I'm just going to say n. So that's 6 over n. Then what I'm going to do is I need a y sub I, right? Like where am I going to find each of these? And then how am I going to do that? So what I'm going to do is I'm going to say that, what do we have here? We have y squared equals 4x. So x, I just like opened some weird thing. Hopefully that doesn't mess anything up. Y squared equals 4x. So x equals y squared over 4. That opens to the right. That's this one here, right? So that's x equals y squared over 4. Let's name this I don't know. I'm going to call it f of y. Like, why not? It's a function of y. And then this other curve is y equals 2x minus 4, but I really want it to be a function of y, so I need to solve for x. So I'm going to say it's y plus 4 divided by 2. So x, let's see here. X is y plus 4 divided by 2. I'm going to call this g of y. All right, so y sub I is going to start at -2, and I'm just going to keep adding delta y. So I'm going to say it is y sub I is -2 plus I times delta y. And then each of these individual rectangles has an area of, this is delta y, delta y, delta y, delta y, delta y, has an area of delta y times how do I get this segment? Well, I want a positive, right? And on the number line, right? If I want to go from 1 to 5, I just do 5 minus 1. Here, I'm going to do the right-hand thing minus the left-hand thing, which looks like it's going to be g of y sub I minus f of y sub I. So one rectangle is going to be g of y sub I minus f of y sub I. That's actually kind of like the base, I guess, if you think the base is horizontal, and then delta y. So what I want to do is I want to do the limit as n approaches infinity of the sum of all these rectangles. So from 1 to n of g of y sub I minus f of y sub I delta y. Now when I do that, I know what's going to happen. What's going to happen is it's going to become the integral from, so what did I do here? Oh, I think I might have, hold on. I may have crashed the app. Well, I may not have. I don't know. We'll find out. So where does y sub I start? It starts at -2 and it ends at 4. So -2 to 4. And then it's going to be g of y minus f of y dy. So what I'm going to do is I'm going to let the calculator do the work to take a lot of the time out of this, potentially. So let's see. Switch to a calculator screen. I don't know what's on my calculator right now. Oh, I guess like our previous. I was doing a little number theory thing, trying to learn some stuff. So I had to, some factoring. I don't know if I ever knew it, but I definitely like learned a way to figure out the number of integer divisors of a number. I had never known that. That was, or maybe I knew that at some point. I don't know. I took like a bunch of number theory classes, but it's like 20 years ago. So who remembers? All right, let's define some stuff. G of y, we said was y plus 4 divided by 2. And then f of y, we said was going to be y squared over 4. So we want to do the integral of g of y minus f of y, comma y, and we're going to go -2 to 4. So we get just straight up 9, which I don't know if I was expecting that. Can we do this in terms of x? I mean, we can. Let's see if we can. I'm going to reproduce the region. So I'm going to do it all in the calculator. I'm going to reproduce the region. So I need to graph y equals 2 square root of x, and also -2 square root of x. Okay, and then I need to graph 2x minus 4. Okay, so that's our region. Hopefully you recognize it. And we can just have the calculator do the work here. So I'm going to do the bounded area. Graph this, and then my lower bound, you can just type them. So I'm going to say 0 and then 1. Okay, and now I have to do it again. Then I have to add those values. So menu 6, 8, this graph and this graph. And we are going from x equals 1. Oh, why are you asking me for the upper bound? 4? I may have messed that up. This is why I don't do this. Menu 6, 8, graph. Click, lower bound 1, upper bound 4. Okay, and if I add those together, I get 6 plus 2 is 8, and then like 2/3 and 1/3, 9. So you could have done it in terms of x, but way easier to do it in one shot in terms of y. That's the advantage of integrating with respect to y. So how do we decide to integrate with respect to y? A vertical line causes us to have to do multiple integrals because the top and the bottom curves are changing. A horizontal line is constant all the way through. The left and the right curve never switch on the interval. And so that's like your hint that you want to integrate with respect to y. All right, I'm going to go back to the notes and then I'll end this video here and come back in the next one and do some more where I think we're like setting them up and doing them. I don't know, it may not be a long video, but this might have been long, so who knows? All right, so we got 9. In general, what you do when you integrate with respect to y is this. So it's almost like the exact opposite, right? So you're going to do the integral from the bottom to the top, the lowest y value to the biggest y value of the region, and then right take away left. So the integrand is right take away left, the bounds are bottom to top. When you integrate with respect to x, it's the integral of top take away bottom from left to right. So it's like a straight up switch. I like it. I mean, you always look really clever when you're doing it, you know, especially to people who don't know what you're doing. Integrating with respect to y, like, oof, wild. All right, so I'll be back in the next one, and I will see you there.